Good afternoon, welcome once again to the third talk of the second week. So, here we are going to talk about partial derivatives and continuity. You might wonder that when I have spoken about functions, as you have learned in the case of one variable calculus, I should talk about continuity of the functions and properties. But here I want to talk about derivatives, because derivatives were always spoken about after continuity. So, why I am speaking about partial derivatives first means the kind of derivative, and then I am talking about continuity. The fact is that partial derivatives can be understood from the knowledge of a function of a single variable, but continuity of functions of more than one variable needs a kind of jump in the imagination, and that can only come later on. Okay. So, what are partial derivatives? So, let me define a partial derivative. Now, first I will define it for a function of two variables, that is I will consider a function from R2 to R, and I will write this function as z is equal to f of xy. So, when I am talking about partial derivatives, I am essentially thinking that this variable y is constant, you can put some number in place of y, and then you take the derivative, thinking that y is constant, you take a derivative with respect to x, because once you think that y is constant, f x y becomes a function of y and as a function of x, and as a result of which you can easily take the derivative, which you know. So, you can do the same thing with x, you can fix up the x and then take a derivative with respect to y. So, when you take a fixed y and take a derivative with respect to x, we say we have taken a partial derivative with respect to x, and the other one the partial derivative with respect to y. So, how do I do it? So, at a given say point x y, the partial derivative of f with respect to x is given as the limit of f. So, I am just changing the x, y is my fixed x plus h y at the point x y, the partial derivative is given as this, partial derivative with respect to x as h tends to 0. So, I am using my knowledge of one variable calculus. So, of course, you can say x naught, y naught and all those things, we calculate that at that particular point. So, if you want to be more precise, you can write this as del f del x evaluated at the point x y. So, if you want to evaluate the partial derivative with respect to y, so what we can do, it is a kind of partial differentiation. So, you do not bother about the nature of the full function, but bother about the nature of only of the part of the function. So, you fix one variable, you vary and keep all the others fixed. So, if you want to talk about n variable now, so you kept say you want to take derivative with respect to x1, x2 to xn you can keep fixed and then do it. So, limit h tends to 0, f of x is now fixed, y plus h minus f x y divided by h, and often we will write this as evaluated at the point del f del y evaluated at the point y. So, this is the way I would like to express, just I have learnt about function of two variables, but when you operate with it, for example, if I take f x y is x square y plus sin y plus x cos y. So, if I do it, then what is my first derivative? So, del f of del x evaluated at any point x y. So, first I think that y is fixed. So, I will have 2 of x into y here, and here there is y is fixed. So, this is constant. So, plus 0 plus here just I take a derivative with respect to x. So, it is cos y. So, this will give me 2 x y plus cosine of y. Now, if I take derivative with respect to x, sorry y, then in the first case I will get x square because derivative of y is 1 plus sin y's derivative is cos y, and here I will get minus x, sin cos y's derivative is minus sin y, keeping x fixed. So, this is exactly two derivatives. You see both f x y, that del f x and del f y are functions of x and y. Now, I am looking at a function of more than one variable. So, now I am looking at f from Rn to R. So, we write this as z is equal to f of x, or if you want to be more precise, you can write this as z is equal to f of x1 plus x2, x1, x2, xn, not plus, sorry, x1, x2, xn. Now, basically for partial derivatives for each I from 1 to n, you can define a partial derivative del f del xi. So, how would you do it? You will just define it in the same way, that del f of del xi is equal to limit of h tends to 0 f of x1 xi minus 1 xi plus h. I am just moving the xi, there is others are kept fixed, xi plus 1 xn minus f of x1 xn divided by h. So, of course, you have to understand that del f del xi is evaluated at the given point x1 to xn, and del f del xi in general is a function of x1, x2 and xn. So, this is basic idea. So, that is already we have studied this kind of things. Now, we are going to talk about limits for function of n variables, limits of multivariable functions. What do you mean? This is a very key issue, and I have spoken when I gave an introduction to the subject. I told you that this is the key fact which will differentiate our game in one dimension and compared to our game in higher dimension. The games differ on this issue. Limits of multivariate functions, maybe I should write that. So, when I am talking about limits of multivariable function, let me first look at a function from R2 to R, that f is from R2 to R, and then let us see what is the meaning of limit in that space. Consider in R2 there is a point given x naught y naught. What do I mean by the expression x y tending to x naught y naught? So, my question is, what does this mean? This is a very key question, and this needs to be understood, because without understanding this idea nothing else can be achieved. You have to understand on the plane of the board that suppose I have a point here, on the plane, and I have a point on the real line. Now, when you are on the real line, your degrees of freedom is only 2, because either you can approach the problem from the right or you can approach the problem from the left, approach the approach the point. So, if this is my point x, or for a point A, then x either approaches it from the right, A plus I would say, or x approaches it from the left, x approaches. So, it is either approaching it from the left or it approaches from the right. If someone don't like this symbolism, one can say x approaches from the right when x goes down, or maybe that is a better symbol, x a plus. I sometimes get confused with symbols. I somehow have, don't bother, I had not got much used to standardizations. But when you come to a point on the plane, just like what I have drawn in the board, x naught y naught, your freedom of movement towards x naught y naught is infinite. Not only that, it is countably infinite, in the sense I can come like this, I can come like this, I can come like this, I can also come like this, I can also come approach it like this, I can come approach it like this. So, when I write the term a function of x y limit when x y tends to 0 0, we need not bother whether the function is defined at x naught y naught, but the function value tends to some place. Then you have to understand, if I say this is equal to L, then it means whichever path I approach x naught y naught, for all such path the limit must be L. If there is one path for which the limit is not L, then we say that the limit does not exist. So, for all such paths, so remember this means for all such paths the limit must be L. So, here as I would like to redraw this thing again. So, many ways of approaching this point, this way, straight, in this way, or in a zigzag way, whichever way, or maybe this way, whatever. Now, we would formally define, just like the epsilon delta definition that you know for functions of one variable, similarly we can give epsilon delta definitions of functions of more than one variable, and for that we need to know how to make a generalization of the delta neighborhood that we continuously have used when we spoke about function of one real variable. You have a look at the one real variable course. So, then let me just go ahead and define what is called a ball of delta radius. So, ball of radius delta centered at x naught. What does it mean? This we write as ball of radius delta, so we will symbolize like this, is given as the set of all x in Rn, we are now talking in terms of Rn, such that the norm, the distance between x and x naught must be less than or equal to delta. This is called the closed ball. It is a sphere with everything stuffed inside it if you are in 3 dimensions, closed ball. So, we are basically writing everything algebraically, but bringing in the imagination what we have till the 3rd dimension, we are bringing it up. So, that is leap in the imagination. So, if you just have one variable here, so mod of x minus x naught is less than delta, so x is lying between x naught plus delta and x naught minus delta. So, if n is 1, then b delta x naught is nothing but x minus x naught minus delta to x naught plus delta. So, that is kind of important, that has to be understood, that this is a true generalization. So, what we need largely is the open ball. And the open ball is something like this, just you do not have the boundary of the ball. So, it is all x in Rn such that the norm of x minus x naught is strictly less than delta. So, if n is equal to 1, if n is equal to 1, then it is very important to understand then what would happen. Then this b delta x naught would be nothing but the set of x in R, and norm now becomes modulus when x minus x naught is less than delta, or it is nothing but the set of all x in R such that x is lying between x naught minus delta and x naught plus delta. So, this another way of writing is this is x naught, the open interval x naught minus delta to x naught plus delta. So, you see this open ball and closed balls are exactly generalizations of the delta closed interval and delta open interval, right. This is the delta closed interval and then this is the delta open, this is the delta open interval. So, this is what we have summarized. Now, this idea of the ball, because the delta ball was required to define the meaning of a limit, these acts as a kind of neighborhoods to a given point. So, same idea, these open balls and closed ball will act as a kind of neighborhood in the higher dimension. So, let me go and write the definition at the general level. Let me just not bother about 2-dimensional thing. You can do text where they will just bother about 2-dimensional things, but I will first I write it in Rn and then we will see what we mean by the 2-dimensional stuff. So, what do we mean by this statement limit x y going to x naught y naught f x y is equal to L. What do we mean by this? This means given epsilon greater than 0, so this is what I am writing in R2 first, then I will write in Rn. So, given epsilon greater than 0, there exists a delta greater than 0 depending on epsilon such that the mod of f x y minus L is less than epsilon whenever x y is not same as x naught y naught and lies in the open ball. So, for this I have to use the norm because we are in 2 dimension, we do not have just mod. Here we are dealing with real numbers, f x y is a real number, right. So, how do I do this? So, given this, this is what happens, this is the definition, right. So, if you for example try to find the limit of, find the limit as x y tends to 0 0 x square plus y square plus 2. Of course, with hindsight you know it does not matter whichever road I come to 0, this x square plus y square would always be 0. So, this answer would be 2. So, this is the kind of ideas that you can use. Now, let us go to higher dimensions. Now, when I come to higher dimensions like f is from Rn to R, how do I speak about continuity? How do I talk about limit? So, what do I mean by limit x going to x naught, where x is a vector in Rn, x naught is a vector in Rn, and that limit is L. This again means the following: given epsilon greater than 0, no matter how small. In fact, my undergraduate teacher used to always use this term, let epsilon be given, epsilon greater than 0 be given, and no matter how small. That sound still, you know, it booms in my ear. He had a very booming voice and it booms in my ear. So, I have also got this, I have also started using this thing that let epsilon greater than 0 be given no matter how small. So, once epsilon greater than 0 is given, we can find an existence of a delta greater than 0 such that for all x element of the open neighborhood B delta x naught, we except the point x naught, the absolute value of f x minus L for all such points, I have this less than f delta, of course depends on epsilon, I have this fact. When I am talking about the limit, x naught may not be defined at f itself, f need not have a definition of x naught. So, this is something we have to keep into mind. If you had a definition of x naught and you have that the limit itself is equal to f x naught, then the function is continuous, and that is exactly what we are going to talk about. So, function say f from Rn to R is continuous if limit f of x as x goes to x naught is f of x naught. In this case, I am expecting f to be defined at x naught. If this is true, then we say that the function is continuous. Of course, we can have an epsilon delta definition. Continuity simply means that if there is a small change in x, there must be a small change in y. If for a very small change in x, there is a huge large change in y, then the function is really not continuous. Continuity crudely means a small change in x must give me a small change in y and a small change in f. So, if you want to write down the epsilon delta definition of this, we just try out the dreaded epsilon delta definition. I do not know why people dread the epsilon delta definition. It simply says that if you give me a very tiny amount and say, okay, if f changes by this amount, tell me the corresponding change of x that is required to affect this change in f. So, it is another way of telling that a small change in f corresponding to a very small change in f, there must be a corresponding very small change in x if the function is a non-constant function. So, this is something already given, already inbuilt in my thinking. So, that is the idea of continuity, that you can really move without taking your pencil off the or pen off the paper. So, if a small change is made in x, the small change is made in y, there is this change is corresponding to some small change made in x, it cannot be corresponding to some big change except a constant function. So, if for a very small change in x, if there is a huge change in y, so that for example, you have a function like this, so for a very small change in x here in this neighborhood, very small change, if it is in this neighborhood, the function values have changed very large, heavily. So, such a thing represents discontinuity. So, this is something very important to understand. So, here if I write it down in epsilon delta definition, it will simply mean given epsilon greater than 0, there exists delta greater than 0 such that for all x element of b delta x naught, here x naught, x could be x naught also because the function is defined at x naught, we have fx minus fx naught less than epsilon. Now, suppose instead of this I consider a function f which is a function from Rn to Rm, capital F, then how do I go about? How do I go about talking about the limit? So, now let me talk about capital F which is a function from Rn to Rm, and I say that the limit x going to x naught, f of x naught is the vector L in Rm. What does that mean? If the vector function goes to some vector, it will mean in a similar way that given epsilon greater than 0, there exists delta greater than 0 such that for all x element of b delta, sorry, x going to x naught, sorry, there is a mistake, please check it, x naught, b delta x naught and without the point x naught, for them the norm of fx minus L, the norm now because it is a vector, so the length, the distance between fx and L must be less than epsilon. Similarly, you can talk about a continuity of this class of functions which I am not writing down anything, because you can write it down. For a continuity also that same story will come, limit of f of x as x goes to x naught must be f x naught, that is f must be defined at x naught. This is, so you are seeking for a point. So, when I am talking about continuity at x naught, I am proving that whenever x is approaching x naught from whichever path, f of x value must go towards, move towards f x naught. The f x as a vector must approach f x naught. Of course, you can look at everything from a component wise point of view. Instead of writing this, you can look at f of x itself as made up of say m parts, and if limit of fx, sorry, limit of fi as xi goes to x naught is some li, and this vector L that you have formed here is nothing but L1, L2, Lm. So, you can do things even for a vector function, but let us now for simple 2 dimensional R2 to R, let us look at a few examples which we must be using an epsilon delta type thing, a very unlikely example. So, here is an example which I am giving from this book, which I again want to show you by Marsden, Tromba and Weinstein, Basic Multivariable Calculus. I again tell you that this book is available in Indian print. It is a very good book and it should be in the library of maths teachers as well as all those who are interested in calculus. They would really learn the subject very well from this book. And those who use multivariable calculus in the research, scientists and engineers, economists specifically, they should actually use this book. So, for example, I would ask if those who have access to MATLAB and all those things can actually draw this graph. So, I am draw this function of 2 variables. So, I am asking you to find the limit of x y going to 0 0 and 2x square y by x square plus y square. It is a kind of very strange situation because here the upper part will go to 0, lower part will also go to 0. So, it is kind of a 0 by 0 situation, but I claim that this limit is 0. So, if you have to show that this limit is 0, I really have to use the epsilon technique. So, let us look at this expression 2x square y by x square y square. This I can write is less than 2x square y by x square. This is the key fact and hence this is less than equal to mod 2 of y. Why it is the key fact? Because you know that x square is less than equal to x square plus y square. So, we are approaching 0. So, we are approaching 0, but we are doing it in such a way that x square plus y square both are not 0. Suppose I am approaching x y equal to 0 0, but through the points where x and y are not 0. Of course, you can approach it through a point where x is 0 and y is non-zero by the y axis. So, in that case I have to use y square here instead of x square. So, whatever, so both are not 0 when I am approaching x 0 0 from all the sides. So, this is valid or y square less than equal to x square is valid, whatever. So, whenever I am very near, basically I am, here is my 0 0 point and I have drawn a small ball of some radius around it, maybe the delta, and when I am here and here and here and here, and whenever x and y are non-zero, that is x y is not equal to 0 0, then I can always write this, and this would imply 1 by x square plus y square is less than equal to 1 by x square, and I get this. So, now choose epsilon to be greater than 0 and delta to be half of epsilon. So, basically what you have is that, now look at all such xy's, which are lying in this ball, that is around 0 0, lying in this ball around 0 0, but not equal to 0 0. Of course, you can say what would happen to points which are lying on the y axis, right? What would happen to points which are lying on the y axis? For example, x is 0. If x is 0 and y is non-zero, the function value is 0 anyway, it is 0 0 0 0 0. So, if you approach it along the x axis, that is y axis towards 0 0, and your y is some fixed value and your x is anyway 0, your function value is anyway 0. So, if you approach along this y axis, right, if you approach along this y axis, then the function values are anyway 0. So, the limit will go to 0 if we approach along the y axis. Now, we have to investigate what is remaining, how we have to approach it along other parts, and in that case x is not 0, and that is why what we have written is true. So, now let this be less than delta, and so this is what, if I do this, this is nothing but norm of x y, which is root over x square plus y square, and that has to be less than delta. So, this implies that y square is strictly less than delta square, which implies, because x square plus y square is less than delta square, which implies that mod of y is less than delta. And then does that means that 2 of x square y divided by x square plus y square minus 0 is less than equal to 2 of y, which is less than equal to 2 of delta. So, and delta is half of epsilon. So, this is nothing but half of this epsilon. So, what I have that 2 of x square plus y square by x square plus y square minus 0 is strictly less than epsilon whenever x and y is within this neighborhood. Whenever it is within this delta neighborhood, I am having this. I am having this fact for all x y. Now, this is true for all x y in the neighborhood. You have to be very careful here. This is true for all x y in this neighborhood, but not for points for where, suppose you have x squared 0. So, you will have here 0. So, you cannot have 1 by y square less than 1 by 0 square, you can't have that. So, so here I am looking at all the points for which, so you know, for all the points which are lying on the y axis, be very careful here, this value is always 0. So, this difference is anyway equal to 0 less than epsilon for whenever x and y, x y is strictly less than delta and y is lying, x y is lying on the y axis. Now, for remaining points we have this inequality. So, for remaining points we have this equality, right, means in this case basically I want to say that x is not equal to 0 and y is not equal to 0. So, and for remaining points you have to run this show that we have just shown. So, for remaining other x y, that is also strictly less than epsilon. So, for the one which is lying in the y axis, this is anyway strictly less than whatever epsilon you choose, for whatever for any point that is lying on the y axis, this is 0. So, it does not matter whatever x y you choose, even it is within that delta neighborhood that you have got or whatever delta you have chosen, for that also it will be 0, 0 is anyway less than epsilon, epsilon is greater than 0. But for all other points where x and y both are non-zero, right, where x is at least non-zero, this story will go through, and hence this is what we will get, right. So, even if y is 0 for example, so it is on the x axis, then also this will be 0. So, for x axis and y axis basically you do not have to bother, because in both cases the function value whether x is 0 or y is 0, this is 0, it will be anyway less than epsilon for whichever be your delta, whichever be the delta neighborhood. But for all other points you have to choose the delta neighborhood in this way and show for all such points also this distance is less than epsilon. So, hence for every x y in this neighborhood, so which now takes points here as well as the points on the axis, this is less than epsilon, that is what it means, and that shows that the limit is 0. So, here we have given you quite a bit of understanding of how things are working. I make you try as a homework. As a homework, maybe I will ask you to do a problem which I take from the book, an example problem which you can try as a homework. So, as a homework you are going to f of x y is xs square y by xs square plus y square. Similar sort of structure you see, if xy not equal to 0 0 is equal to 0 if xy is equal to 0. So, it means that this function is defined in segmented way. Now, I am showing that you have to show that f is continuous at 0 0, continuous at 0 0. One must be very cautious here again when you look into this case, be very cautious again. So, if either x and y are 0, I am repeating, this value is anyway 0 always. So, this distance, this minus 0 would always remain 0 whenever x and y, any one of them are 0. When both are non-zero, then all this machinery that we have done will work. So, this is only when both are non-zero. So, when both are 0, so we should write on the side when either x equal to 0 or y equal to 0, 2 x square y by x square plus y square is equal to 0, and automatically things holds, automatically things holds. That is it. So, you have to be careful while you make arguments, you have to be extremely careful when you make arguments, you have to see, first you check what happens along x axis, y axis, whether through that x axis, y axis your arguments are all right, then you check out what are the other points. So, here this delta is actually for the points where x, y both are non-zero, because for the x axis, y axis as we showed things are 0. I am repeating it because you need to be very careful when you are looking into this kind of things. I was just talking about y axis when I was explaining it, but it was also true for x axis. I just missed that point that I should have spoken about both x and y axis. So, anyway, you have the thing right in front of you, you go through this example very carefully. It is a very simple application of the epsilon delta thing. So, if I am just to look at this thing, how do I decide? The only way I decide is in this way. So, what I do, I take the limit. Here only this is a function of one variable, limit y goes to 0. So, what happens, suppose I want to just calculate the limit. So, I take this one and I know this is less than this. So, when I take the limit of this must be less than limit of this, but limit here there is no x, there is only y. So, this because it is single variable, limit this y, this limit goes to 0. And so, limit of this, so what would happen, limit of xy goes to 0 0, norm of 2x square y by x square plus y square, that would actually go to 0 0, and that would be exactly 0 0. And a very important result about limits is that this is a trick that you should always learn, because this is a fact about limits, that if with the mod itself is a continuous function. So, the limit and the mod can be changed, right, limit and the mod can be changed. So, you can put the limit inside. So, limit of this, mod of that would be 0. So, limit of that would also be, sorry this is 0, I am making a mistake, not 0 0, it is 0, it is a numeric number 0. So, if you have a continuous function, a very important criteria about continuous function is this, that limit fx, right, as x tends to x0 is fx0. Now, the modulus of a function of a number, of a real number, this is a real number, is a continuous function, and you taking the limit. So, modulus of fx, f could be the modulus of x, this is a real number, right? It is a vector, right? xy is a vector, you are taking the modulus of that. So, this is a real number and you are taking the modulus of that going to 0 0. This actually means the same as this is something important to remember. So, basically you can change the modulus and the limit. So, by the from the definition, because you can actually this is the definition of the continuous function. You can, using this definition, you can show that you can make this change. From here you can show, I am not getting into the details, but you can show that this change has been made. So, if this is equal to 0, you have limit. So, when you want to compute the limit by hand, not by epsilon delta. So, this is a real number which is equal to 0, modulus is 0, so it must be 0. So, with this I end my talk here and hope that all these things that I am trying to tell you here is told in much easily in terms of sequences in R2 or sequences in Rn. We will have a chance to speak a bit about them. I do not know whether I will really have a time to, but then that takes me more into the direction of analysis rather into keeping you grounded in calculus, but let us see. But just take it from me for the moment that you can really use this idea to show this thing, and hence you can compute the limit in this way. Thank you very much.